Good morning, students. You're welcome to AAE 468 Advanced Orbital Mechanics Video Lecture 4. Today is the 27th of February 2015 and the time is 1:44 a.m. We're going to be starting from where we stopped the last time, with the last video lecture. And this video lecture is going to be a rather short one. Because we are just finishing with the slide, with this present slide, and I've included some videos from the internet which you will be watching alongside after this video lecture. So we'll go to where we start. So prior to this slide, we looked at the transformation between geocentric, equatorial, and perifocal frames. We looked at the transformation matrices. We saw that when you want to go from when you have the state vectors in the perifocal frame, you can get when you have it in the geocentric equatorial frame, that is our geocentric equatorial frame, you can get it in the perifocal frame just by multiplying what you have by the transformation matrix from geocentric to perifocal frame. So that's for the position vector. The same can be done for the velocity vector. And when you have the state vectors in the perifocal frame, that is this and that, you can always go to the geocentric equatorial frame by multiplying what you have by the transformation matrix from the perifocal frame to the geocentric equatorial frame. So today we'll be looking at the effects of the Earth's oblateness. Normally, in the elementary years, elementary years at the secondary school, you always say that the Earth is a sphere. But now we have to acknowledge that the Earth is not a perfect sphere. It is an oblate spheroid. And it is not a perfect sphere because it bulges out at the equator because of the centrifugal forces arising from the fact that it is spinning about its axis. This just means that the equatorial radius is larger than the equatorial radius is larger than the polar radius. So the lack of symmetry means that the force of gravity on any orbiting body around the Earth is not directed towards the center of the Earth, because if the Earth were perfectly spherical, then the force of gravity would be for any position on the Earth, or the force of gravity on an orbiting body at any position of the Earth will be directed towards the center of the Earth. But then it is not the case because the Earth is not a perfect sphere. So the flattening of the Earth at the poles is called oblateness, and it is defined as the ratio of the difference between the equatorial radius and the polar radius, and then the equatorial radius. So you find this difference and divide by the equatorial radius, you get the oblateness. And the Earth is not the only planet which is oblate. Some other planets are also oblate. That is, they have their equatorial radius larger than the polar radius. The gravitational field of a perfectly spherical planet depends on the distance from its center, with Newton's law of universal gravitation. But because of the oblateness, some variation with latitude can also be seen. because what we are saying is because of the obliqueness, the radius of the Earth will be varying from its maximum at the equator to its minimum at the poles. So obviously, since the force of gravity is a function of distance to the center of the Earth, since the distance is now varying, that means the force of gravity will also be varying. So the variation due to the latitudinal position on the surface of the Earth, or not on the surface of the Earth, because sunlight will be on the surface of the Earth. It won't be on the surface of the Earth, or due to the latitudinal position around the Earth, is called the zonal variation. And the dimensionless parameter J2, which is referred to as the second zonal harmonic, is used to quantify the effects of the obliqueness on orbit. J2, of course, varies with planets. There's a list of the variation of J2 with planets of the solar system in the textbook. So, looking at the equation for the motion of this satellite around the oblate Earth, we see that we just have an extra term here. It takes care of the perturbation of the motion of the satellite around the Earth, because as you may have been able to identify, this is, leaving this apart, this is just the two-body problem. That is the equation of the two-body problem. And that was the case for when we were considering the Earth to be a perfect sphere. So now that we are taking into account its obliqueness, we need to add an extra term here, which just takes care of such effects from the obliqueness. This extra term, in comparison to this other term, is very, very small, very, very small. But then it has a significant effect as well. So the perturbing acceleration has components in three directions. That is, it has some components in the radial direction in the orbital plane, and some components in perpendicular to the radial direction, and then some components in the angular momentum vector direction of the orbital plane. And then the components in all the directions are directly proportional to the dimensionless parameter J2, which is the second zonal, what did we call it? Second zonal harmonic. The second zonal harmonic. So with these equations, we see that the components of the perturbing acceleration are functions of J2, and the orbital elements that we are already familiar with. Some of the orbital elements that we're already familiar with, such as the inclination, argument of the perigee, the true anomaly, and of course it's also a function of the radius of the Earth or the planet, or any other planet that we may be concerned with. Of course, this will be the equatorial radius. And then the perturbing acceleration also induces some time rates of change in all the orbital parameters. For example, the time rate of change of the right ascension is given by the equation here, and the time rate of change of the argument of the perigee is given by the equation here. We can see from here that the time rate of change of the right ascension has just or is a function of just the components of the perturbing acceleration in the direction normal to the orbital plane, but the rate of change of the argument of the perigee is dependent on all components of the perturbing acceleration of the perturbing acceleration. So if we can integrate the time rate of change of the right ascension over one complete orbit to have the average of the time rate of change. So when that is done, so we have equation 4.47. We see that we can observe that if the inclination, I is the inclination of the orbit, if the inclination of the orbit is less or equal to greater or equal to 0, less than 90 degrees, that is, if I is equal to 0, we have cos 0, which is 1. We see that the time rate of change of the right ascension is going to be negative, or if it were 90, of course, if it is 90 degrees, this is just going to make the whole thing go to 0. So we are just looking at the case where the inclination is between 0 and 90 degrees. So what this just means is that in that case, the node line is going to be shifting westwards. That is, there's a negative change in the right ascension. It's moving. You recall that we measured right ascension positive eastward of the vernal equinox line, but for an orbit inclined at an angle between 0 and 90 degrees to the equator, to the equatorial plane, the time average of the change in the right ascension is negative. That means the node line is going to be moving towards the vernal equinox line. It's going to be moving westwards. But when we have I greater than 90 degrees, I greater than 90 degrees, but less or equal to 180 degrees, we are going to have this equation 4.47 to be positive. That means the node line is going to be moving away eastwards from the vernal equinox. And that is, so the first case is for the prograde orbit. This must have been a typographical error, or maybe it was an old term they used to call it, but it is prograde, not postgrade. It's prograde orbit. That means the inclination is between 0, is equal to 0 or greater than 0, but less than 90 degrees. For retrograde, it is greater than 90 degrees, but less or equal to 180 degrees. And here, when we, like I said, when I is equal to 90 degrees, this just goes to 0. And what it means is that there's the right ascension of the orbit is just constant. So that means the node line is stationary. So, and this is just some pictures I got from the internet to use to explain to you what a prograde orbit is and what a retrograde orbit is. So if that is the Earth there, if you have an orbit for a satellite with an inclination 0 degrees, that means the orbit is just coincident with the equatorial plane of the Earth. So that is a prograde orbit. Then you can now have orbits inclined to the equatorial plane, that is having I equals some angle less than 90 degrees. So when if we were to draw it on this image, it will be something like that. It will be something like that. So that's a prograde orbit. So when you have the orbit inclined at angles greater than 90 or less or equal to 180, that means the orbit is just going to be in that manner, in the other direction. So that's a retrograde orbit. So in a similar fashion to what we saw with the time rate of change of the right ascension, we can also look at the time rate of change of the argument of the perigee. And that is given by equation 4.48 here. The expression shows that when the inclination angle is greater or equal to 0 degrees but less than 63.4 degrees, or when it is greater than 116.6 degrees or less or equal to 180 degrees, that we have the time rate of change of the argument to be positive. It just means that the perigee is moving forward in the direction of the motion of the satellite. And then when we have the inclination to be greater than 63.4 degrees but less or equal to 116 degrees, the perigee regresses, moving opposite to the direction of motion of the satellite. Or when I equals 63.4 degrees and 116.6 degrees, the absolute line does not move at all. So figure 4.18 gives a plot of equations 4.7 and 4.8. That means the time rate of change of the right ascension and then of the argument of the perigee at low inclinations. For it, the orbit is near the equatorial bulge for longer. The effect of upneatness on both the time rate of change of the right ascension and then that of the argument of the perigee is rated at low inclinations. That is, we can see from here that at low inclination, that is particularly around 0 to 20 degrees, we can see that we have much effect much effect of the change in the right ascension. Like for 0 degrees, it's around minus 8 point something. But as you move away from the equator, that is, as the orbit gets more and more inclined to the equator, the omega naught starts decreasing and moving towards 0. And when it is 90 degrees, it is just equal to 0. The same can also be observed with small omega dot here. And just because as the orbit moves away from the equatorial bulge, the effect of the equatorial bulge starts waning off. So the effect also decreases with increasing semi-major axis because the satellite becomes further from the bulge and its gravitational influence. When omega naught equals one big omega naught equals small omega naught equals 0, it means J2 is also equal to 0. There is no equatorial bulge. That is at the poles. Or for a planet that is perfectly spherical. The time average rates of change for the inclination, eccentricity, and semi-major axis are all 0. The effect of the objectness of the Earth can be taken into advantage or has been taken into advantage in the design of sun-synchronous satellites and the Russian Munia satellite constellations. The next thing I want to show to you here, or that I want you guys to view, are these videos. I'll also be sending them along with this PowerPoint slide. They I've gone through them and I've seen that they are quite instructive in the subject of orbital mechanics. All that we've been talking about are captured, and then you can have a feel of some kind of practical sense of all the equations which we've been talking about before. So make sure you watch the videos and also the examples in the some of the examples in the textbook here. Make sure you go through them, and any problem you have with them, we are going to discuss them when we have the question and answer session. So go through example 4.5, this, and then example 4.6. Well, with example 4.72. So example 4.5, 4.6, and 4.7. And there's another one. So example 4.5 to 4.9. Go through them, and then when we have the question and answer session, whatever problem you have with them, let me know. So this is the end of this slide and the end of this video lecture. In the next slides, we start with preliminary orbit determination. So we just finished with chapter 4 and we'll be going to chapter 5. So make sure you go through the examples and then watch the videos as well. Okay. Thank you.